Okay. Welcome back to the third, and I am very, very dedicated to this being the final video for our energy notes. I left you thinking about a diagram for converting between potential and kinetic energy. The pendulum is one of our favorite diagrams for this. You can also use, I know we did the roller coaster simulator. This has potential energy too. I think we'll do a skate park simulator. You can do that as well, as long as you're not putting energy into the system. So if you envision a closed system like a pendulum or a skater that's not pushing, or a rock rolling down a hill, whatever you want to envision with the energy not entering or leaving the system. So we're ignoring friction. We're ignoring real life, basically, with this pendulum. Then, if you do all of that, it's going to have the most potential energy at the highest points. And when it's the highest up, it's all going to be potential. Everything's potential. If you envision a pendulum going back and forth, a lot of you play around with my Newton's cradle. At that highest point, it can't go any higher, and it stops for like an instant. For an instant of time, it's at zero velocity and has all potential. And then it starts falling back towards the center. And at the very bottom, it can't fall any further because of the string. So all that potential energy from up here has become kinetic energy. It's in the fastest motion it can be in before it heads back up. And then somewhere in the middle, it has a little bit of a mix of both. So that's what I mean by conversion of energy. And we can actually, if you know when the most potential is or when the most kinetic is, we can convert between those two in stories, and we will do that in class. No, you can't lose energy. It can only transfer. Sometimes it leaves the system. Sometimes it goes somewhere completely separate. Think of the sun throwing off all that energy into space, leaving the sun, leaving the solar system even, but it does go somewhere. Cannot be created or destroyed if you want to think of it that way. And the amount of energy stays the same within a closed system that's called closed system. Tried to hit too many buttons there. Okay, last topic here. Conservation of energy is work and power. Work and power equations will not be on the test, but they will show up in a couple of our labs. And you do need to know the theory behind how we can transfer energy at a slower rate or over a larger distance in order to maybe save ourselves in a car wreck or in an egg drop. Egg drops where we'll do with this. So work is how force is applied to an object that actually moves it. Work is a transfer of energy. So when we talk about doing work, actually like physical work, not like mental work like you are doing right now, but physical work of moving your pencil, there must actually be motion. It must actually move in order to do that work, in order for energy to be transferred. Work is calculated by using an equation, which is not on the test, but I'm just throwing it up here for you to know. Force times distance. Force in newtons, just like we did, distance in meters. Work is, once again, energy. Work is a measure of energy, transfer of energy, so it is measured in joules. And we'll use this equation in our egg drop lab to try to save an egg, even though we drop it from 3 meters up in the ceiling, or to think about car crashes and stuff like that. Very similar to our power equation. Power, if you heard about it, we'll do a lot more with power in our next unit, but I wanted to bring it up since it is relevant. Power is the rate of doing work. So it's just basically work times over time. So it requires, to do more work, requires more power, at least in the same amount of time. But you can do less time, same amount of work, and increase your power. So once again, we're distance or time. So if you increase the distance or increase the time that something happens over, you could decrease the amount of energy that's transferred all at once. So instead of going from an instantaneous stop, a car hitting a brick wall, you might think of like a car hitting a cardboard, a stack of cardboard, or your bumper kind of cushioning that blow, or in our egg drop lab using some paper contraptions to increase the distance / decrease the time. So that's what our power. Power does have an equation, once again, on the test, just so you know it. It's work divided by time. Energy's all around us. That's the last thing I'll leave you with. Everything is energy. Think of some stuff. Light bulbs, we use wattage all the time in light bulbs. Your phone uses energy. Electricity is our big form of energy right now. Coal